When the first AI winter arrived, many believed the dream was over. Funding vanished, research slowed, and artificial intelligence faded from headlines. For a moment, it seemed as if the promise of thinking machines had been nothing more than a scientific illusion. But one idea kept the field alive: expert systems. Instead of trying to recreate human intelligence, researchers focused on something more practical: capturing the knowledge of human experts. These systems used large sets of rules, if this then that, to make decisions in narrow domains like medicine, chemistry, and engineering. In the late 1960s and early 1970s, programs like Dendril showed that computers could assist scientists by analyzing complex data and suggesting solutions. It was a different vision of AI, not thinking machines, but specialized advisors. During the AI winter, expert systems became a lifeline. They delivered real-world results, convincing companies and governments that AI still had value. But their success came with limitations. They were expensive to build, difficult to maintain, and unable to learn on their own. In the mid-1960s, the researchers at Stanford created Dendril, often considered the first true expert system in artificial intelligence. Designed to help chemists identify unknown molecules, Dendril combined scientific knowledge with logical rules to mimic expert reasoning. Instead of learning from data, it relied on carefully encoded human expertise. The system proved that computers could assist specialists in real scientific work, laying the foundation for later expert systems like MyCN and marking a major step toward practical AI. By the 1980s, expert systems had moved from research labs into real companies. Thousands were deployed across industries like finance, manufacturing, and medicine. Estimates suggest around 2,000 working systems by the late 1980s, with many more in development. Investment surged as businesses rushed to adopt AI tools, creating a market worth hundreds of millions of dollars and growing rapidly toward the billion-dollar range. Companies like Digital Equipment Corporation reported saving tens of millions of dollars per year using expert systems, fueling massive optimism and helping trigger the AI boom that would eventually lead to another AI winter. In 1982, Japan launched an ambitious national AI effort known as the Fifth Generation Computer Systems Project. Backed by the Ministry of International Trade and Industry, the goal was to build massively parallel computers designed for artificial intelligence and logical reasoning. Over roughly a decade, the project invested around 57 billion yen, about $300 million, and created the Institute for New Generation Computer Technology to lead the work. The announcement shocked the global tech industry and sparked fears that Japan might dominate the future of computing. In response, American companies formed the Microelectronics and Computer Technology Corporation, or MCC, a research consortium launched later that same year. More than a dozen major firms pooled resources, with budgets estimated at $50 to $100 million per year, hoping to accelerate AI and advanced computer research together. Although neither effort delivered the AI revolution that had been promised, both projects reshaped global research strategy, marking a moment when nations and corporations began treating artificial intelligence as a technological race. In 1986, artificial intelligence received new momentum with the rediscovery of a learning method called backpropagation. Although the idea had appeared earlier in different forms, researchers David Rumelhart, Geoffrey Hinton, and Ronald Williams demonstrated how it could efficiently train multi-layer neural networks. Backpropagation allowed errors to be sent backward through a network, adjusting internal connections so the system could gradually improve its predictions. This solved a major limitation that had stalled neural network research for years. While expert systems relied on handwritten rules, backpropagation offered something different: machines that could learn from data. The breakthrough helped revive interest in neural networks and laid the mathematical foundation for the deep learning revolution that would emerge decades later. By 1988, expert systems had become a serious business investment. The market was valued at roughly $400 million, up from only a few million earlier in the decade. Large corporations were spending heavily on internal AI teams, and by the mid-1980s, companies worldwide were already investing over $1 billion into AI projects, much of it focused on expert systems. Optimism was high. Many believed these rule-based systems would soon transform entire industries. By 1987, researchers began shifting from rigid rule-based AI toward a new idea: probabilistic learning. Instead of assuming the world could be described by perfect logic, scientists embraced uncertainty using probability to model real-world decision-making. Methods based on Bayesian statistics allowed machines to weigh evidence and update beliefs as new data arrived. This marked a growing transition toward what we now call machine learning. Researchers explored decision trees, statistical pattern recognition, and early learning algorithms that improved through experience rather than hand-coded rules. While expert systems still dominated industry, probabilistic approaches quietly laid the groundwork for modern AI, moving the field from fixed knowledge toward systems that could learn, adapt, and reason under uncertainty. As artificial intelligence research expanded, scientists began emphasizing standardized benchmark problem sets to compare algorithms more objectively. Instead of relying on isolated demonstrations, researchers used shared datasets and test problems to measure performance across learning methods. These benchmarks included pattern recognition tasks, speech and handwriting experiments, and structured reasoning challenges. The goal was simple: make AI research measurable and repeatable. By testing systems on the same problems, the field could move beyond hype and evaluate real progress. This shift helped push machine learning toward a more scientific, data-driven discipline, setting the stage for the benchmarking culture that later defined modern AI research. In the late 1980s, artificial intelligence began embracing probability as a way to handle uncertainty. One important development was the growing use of Markov models, mathematical systems that predicted future events based on current states rather than fixed rules. They proved especially useful for speech recognition, language processing, and sequential data, areas where strict logic often failed. At the same time, researchers introduced Bayesian networks, a new way to represent relationships between variables using probability. Instead of hard-coded rules, these networks allowed AI systems to reason under uncertainty by updating beliefs as new evidence appeared. This was a major conceptual shift. Machines could now make informed guesses instead of relying only on deterministic logic. Together, Markov models and Bayesian networks helped move AI away from brittle expert systems and toward statistical learning, laying key foundations for modern machine learning and probabilistic AI. At the same time, a different idea about learning began to shape artificial intelligence. Instead of relying on rules or labeled examples, researchers explored reinforcement learning, a method where machines improve through trial and error. An AI system would take actions, receive rewards or penalties, and gradually discover better strategies over time. Inspired by psychology and decision theory, the approach suggested that intelligence could emerge from interaction itself. Computing power was still limited, but the concept introduced a powerful vision: machines learning from experience, much like living organisms do. By the late 1980s, the optimism surrounding expert systems began to fade. Companies had invested heavily in AI, expecting rapid transformation, but many systems proved expensive, difficult to maintain, and limited outside narrow tasks. As the technology failed to meet growing expectations, funding declined, and commercial interest cooled. This period became known as the second AI winter. Research groups shrank, investment slowed, and artificial intelligence once again lost its place at the center of the tech world. Yet, beneath the slowdown, important ideas continued to develop, especially in machine learning and probability, quietly preparing the field for a future comeback. Once again, the cycle had repeated itself. Grand promises of machines replacing human intelligence had drawn enormous investment. And once again, reality fell short. The excitement faded, the funding dried up, and AI slipped back into the shadows. In the next, final chapter, we will move from the 1990s to the present day. Through the rise of machine learning, the explosion of data, and the deep learning revolution that changed everything. And as AI enters our lives more deeply than ever before, one question begins to loom again. Are we witnessing the beginning of something permanent, or moving toward a third AI winter?